Okay, welcome everybody to tonight's public lecture. I'm Emma Matthews from the Geological Society of Australia ACT Division branch and also the Research School of Earth Sciences. And I'm going to introduce Brad. First, I would just like to acknowledge the first Australians on whose land we meet and whose cultures, which are among the oldest continuing cultures in human history, we celebrate. I would like to thank Francis, Patricia and Caroline from Communications for helping to organise tonight's talk. So our speaker, Brad Opdyke, graduated from Columbia University with a bachelor's degree in geochemistry in 1984. He then moved to the University of Michigan where he earned a master's degree in geology in 1987 and a PhD in 1990. His areas of study concentrated on marine chemistry and carbonate rocks. Brad's research has spanned paleoceanographic studies from the Cretaceous to the Quaternary. He is also acknowledged to be a global expert on ocean acidification. So without further ado, I'd like to introduce Brad Opdyke to present Global Climate Change Perspectives from the Past.
And thank you all for coming. I have been at the ANU with first the Department of Geology and now the Research School of Earth Sciences for 16 years now. And this is the first time I've given a public lecture, I think. No, that's not true. I gave one other, sort of, but outside the auspices of the ANU. And I am a paleoceanographer and paleoclimatologist. And the first studies that I did were actually of surface water CO2 exchange in the Southern Ocean. So CO2 and climate and carbonate rocks, which, if you look at them closely and carefully, can yield climate data, have been a part of my career, a very, very strong part of my career. But I'd like to start with this. Because when I see debates about climate in the newspaper, it often occurs to me that most of the people that are debating climate don't even know what climate is. So can I have someone in the audience, perhaps? Give me a definition of climate. Oleg.
The long-term weather pattern in an area average over a time period is, say, 30 years.
Thank you, Oleg. Oleg's a bit of a plant. He's a student of mine. Yeah, so environmental conditions integrated over a time scale of decades, 30 years or so. That would be the minimum. And certainly the time scale of the records that I look at are centuries to millennia. So that's real climate change. And so when people start quibbling about whether this year was warmer than the last year, it reminds me of weather. And some people arguing about whether summer is not going to become, because it's springtime and today was colder than yesterday. And so it's that kind of analogy which frames the debate sometimes within the popular press, which I don't think is appropriate. Here's one of the really, really good websites that you can go to. There's a NOAA website, and every month they'll give you a state of the climate analysis, kind of like State of the Nation address. And it's wonderful things. I just want to highlight the first highlight there. And this is just from our previous month of 2010, March. Combined global land and ocean surface water temperatures, or just surface temperatures, for March 2010 was the warmest on record at 13.5 degrees C, which is 0.77 degrees C higher than the 20th century average of 12.7. This is also the 34th consecutive March with global land and ocean temperatures above the 20th century average. 34th consecutive and counting. So I'm going to start the talk with a bunch of happy facts. This is the first happy fact. Then I'm going to go through a rogues gallery, basically, of people who have influenced me in terms of the climate debate, and I suppose were some of my lecturers and influences in terms of paleoclimate studies. And they're also the people that I introduced my students to when I first had them study paleoceanography. And for the first part of the talk, I guess if you were to fall asleep right now, I want you to take away this message that if we weren't buggering with the climate would be getting cooler. And I'll hopefully show you why that is the case. And that sort of forms the basis of most paleoceanographers and paleoclimatologists' understanding. Here's one of the culprits for the recent warming is carbon dioxide concentrations at Cape Grim, Tasmania. CO2 is a greenhouse gas. It would be very difficult to increase CO2 without having global warming. The physics of this is very, very clear. Here's the mean temperature trend in Australia. Have a little local flavor. So we have some areas in Australia have experienced warming since 1960 of 0.4 degrees C per decade, resulting in total warming over 5 decades of 1.5 to 2 degrees C. Here's rising mean sea level around Australia. So it's all happening. Here's one of the real stars in terms of just science at ANU, a guy by the name of Graham Farquhar. And I was fortunate to have a bunch of just very, very informal, I suppose, just discussions about climate change and things like that, and carbon cycle modeling, which is something I do. Graham attacks it from a different angle, which has to do with plants. And from a biological point of view, CO2 is a good thing. The more CO2 you have in a greenhouse, the faster the plants grow, the less water you need relative to temperature. You need to water the plants. So if that were the only thing that were happening, we'd all be cheering CO2 increases. And Graham travels a lot, and he talks to a lot of the people that were my mentors. A guy by the name of Wally Broker is one of them. And he would talk to me and he'd say, Brad, why is it that paleoceanographers, paleoclimatologists, as a group, are so concerned about human-induced climate change? And so this talk is going to be an attempt to try to give you a flavor of why that is. So what tools do we use to analyze climate change? One of the first ones was the use of stable isotopes. And of course, the use of stable isotopes only came along after basically the creation of the bomb in the Manhattan Project and the development of mass spectrometry. And so the example I've got there shows you the difference between O16 and O18. And just as for those of you that aren't familiar with stable isotope analysis, we ratio the heavy isotope, or the more massive isotope, to less massive isotope. And we get a ratio relative to a standard. And so when we talk about delta 18O, we're talking about changes in that ratio. And so if it's more positive, that means you've got more 18O in your compound. If it's more negative relative to the standard, it means you've got less 18O in your compound. And this ratio is temperature sensitive. One of the things that, and this was the dominant proxy that we used for paleoclimate for a long, long time. Over the past decade or so, we've gotten much more specific paleotemperature proxies than delta 18O, but this was the first one. And the reason it's very, very good is that it is temperature sensitive, and particularly with respect to calcium carbonate, and it's inversely proportional to temperature change. So as temperature goes up, the ratio of 18O to 16O goes down. There are a few caveats, though, that complicate the picture, and that is salinity, but the most important caveat there is actually ice volume. This is Cesare Emiliani, a very young Cesare Emiliani from the 1950s. And Cesare Emiliani came out of the University of Chicago School of Mass Spectrometry. Cesare actually got 2 PhDs. He did one in paleontology, and then he did one in physics and mass spectrometry. And he was part of Harold Urey's group at the University of Chicago. And then he went to University of Miami. And he was the first person to use carbonates, planktonic and benthic foraminifera to make a time series of global temperature change over a long time period, on the order of 500,000 years. And this was the time scale he produced. And this is a paper that was published in 1955. And this is actually a record of Delta 18O from the Caribbean, which he interpreted to be mostly influenced by temperature change. He probably didn't get the ratio of ice volume change versus temperature change right, but he did get a lot of things right. One thing he couldn't get right was the time scale. And to really figure out what was going on with that temperature change and what was forcing that temperature change, you needed to work out what was going on with geologic time over that 500,000 years or 300,000 years that he was looking at. For those of you guys who are scholars of glacial geology, the Wisconsinian, the Sagamon, Illinoisan, Kansan, Nebraskan are the four big glacial advances in North America. And they have their equivalents in Europe, which are the Worm, Rees, Mindel, Gunz advances out of Switzerland, really. These are moraine deposits that go out into southern Germany. And so he was trying to pull these terrestrial data together with the marine data. This became the touchstone for climate change from 1955 until the early 1970s. When this guy came along, who happens to be my father, and he was the first person to actually put together a valid dating tool for soft sediments in the deep sea. And these reversals in the Earth's magnetic field had been dated by various scientists, like scientists here. There's a very famous potassium-argon and argon-argon dating person by the name of Ian McDougall, who worked on dating these specific reversal events. So these reversals had all been dated in volcanic rocks. And so my father had this time scale, and he went to Cesare Emiliani and he said, Cesare, I've got this time scale. Would you like to collaborate in putting together a planktonic foraminifera climate record with the geologic time scale that I've developed here? And Cesare refused. He said, Neil, you can pick your own forams. Cesare had, for some reason, he published a lot, but one of the things that was interesting about Cesare was that he almost published exclusively sole authors papers. He refused to collaborate with people to that extent. My father was not interested in picking forams, and he was very fortunate that a young physicist who decided he was going to look at paleoceanography, but from actually following what Cesare Emiliani had done, by the name of Nick Shackleton. And Nick got his PhD in 1967, about the time my father published that first record of reversals in deep sea sediments. And Nick came to Lamont Dougherty at Columbia University in the early 1970s, and my father asked Nick Shackleton whether he'd be interested in putting together a time scale, and Nick said yes. And so they produced a number of time series over the years, but this record, which correlated the Delta 18O change with the Earth's reversals in the Earth's magnetic field, which of course had been precisely dated, gave paleoceanographers an opportunity to get a real handle on the time scales at which these fluctuations, these regular sort of heartbeat-like fluctuations in Delta 18O took place. This nomenclature, by the way, of 1, 2, 3, 4, 5 is the same one that Cesare Emiliani introduced. And so when I'm teaching about paleoceanography to my students in class, we still talk about stage 1, stage 2, stage 3, stage 4, stage 5. That's still part of our nomenclature, and that goes back to Cesare Emiliani. You'll notice that this scale is going up here from -1 to -2. That's because it's that inverse relationship between Delta 18O and temperature. And so paleoceanographers always plot their data in that respect so that temperature is going up, or the relationship with temperature is going up. So where do we go from here? We've got the data set, we've got a time scale, and this is where the relationship with Milankovitch cyclicity comes in. Now, Milankovitch had published the possibility of an external forcing to Earth's climate, I guess it was about 50 years before these particular publications took place. And he was a mathematician, and he just worked out that the axial tilt of the Earth would be varying on that kind of scale. You get this precessional rotation, like the top rotating on a desk, a gyroscope. And so that's the precessional movement. This has a frequency of about 40,000 years. This has a frequency of about 20,000 years. And then there's the ellipse of the Earth's orbit around the sun, which changes in about 100,000 year time scale, and we'll show you that in just a second. The next rogue in this gallery was another one of my father's colleagues at Lamont by the name of Jim Hayes. And he also ended up collaborating with Nick Shackleton and John Embry. And John Embry was the one that really carried the torch for talking about Milankovitch cyclicity in paleoceanography. But Jim Hayes was the first person to write this seminal paper on the pacemaker of climate change, or geologic time or quaternary climate change, ice ages over the past 500,000 years or so. That sort of realization, I think they published this paper in about 1975 or 1976, that was profound. That not only do we match up these climate cycles using the harmonics of the precession, the obliquity, the eccentricity of the Earth's orbit to these climate variations, but it was also clear from the data that we'd reached a peak back in the early Holocene. The early Holocene would be a period between about 6,000 years ago and about 10,000 years ago. And so every paleoceanographer worth their salt knows that 90% of the paleoceanographic records that we have show a cooling from 6 to 10,000 years ago to sort of the recent past, which would be within the last several thousand years. Often we miss the top several thousand years because of our coring techniques in the deep sea, so we didn't collect that. But that realization was very profound, and it's probably the underlying reason why we as a group really are worried about climate change, because we understand that these forcings, the astronomical forcings, if we kept going on trend like we have for the past several million years, actually we've got really good Milankovitch-tuned records going back tens of millions of years now. If that's going to hold up, then we most certainly would be cooling down. And so even though it sounds silly now to see Jim Hayes standing up there saying that the Hudson Valley will be full of ice again, that was the profound realization that indeed this cycle will continue, and wow, this is going to happen. We could have 2-3 kilometers of ice over top of New York again. And in fact, I used to have a cartoon, which I couldn't find for this talk, that was published in the New Yorker about 1983-84, where you had two of these old prophets in a robe with a beard, one carrying a placard saying, "The end is nigh due to the next glaciation," and the other guy walking in with a placard saying, "The end is nigh due to global warming." And so you get these conflicting views, I suppose, going out to the general public about what's going on in terms of the Earth's climate. And here we have actually what some of these wiggles look like in terms of these astronomical tunings. And they look a little like radio frequencies, except for maybe the eccentricity. And what these guys found was that if you looked at the solar forcings, which vary over the latitude you look at between 55 and 65 degrees north, they found that that correlated the best with the climate data that we had. And of course, this big white blob, you may not recognize it, is supposed to be the Laurentide ice sheet, which is the big ice sheet, which is actually bigger than the Antarctic ice sheet, that used to be sitting over North America 20,000 years ago. It's a big bunch of ice. When that big bunch of ice was there, sea level was down 125 meters relative to today. Huge changes. Canberra was periglacial. Average temperature in Canberra was about -9 degrees relative to what it is right now. It was dry, it was dusty. Not a real happy place to be. Whenever I sort of think about that, makes me more impressed that the original Aboriginal custodians of this landscape actually survived here, because it would have been a hard job. There were sand dunes that were just drifting over the Clyde Mountain. So, there you have the context that we all sort of start from as paleoclimate scientists. And this is our Land Rover. This is the kind of thing we go out and collect our data with. This is the Marion Dufresne. This is the real luxury Land Rover. This is the French one. This is the one where they serve French wine and food at night. They aren't quite so strict about the old dry boat policy. It just wouldn't be French. And you can take some very, very long cores from that ship. And this just happens to be one of the long cores that I've analyzed from off the northwest coast of Australia. This is my data here, going back about 500,000 years, compared to the Vostok ice core data. And even the uninitiated can look at those correlations and see the relationship between the ice cores and a tropical marine core that is giving you the Delta 18O data. So you're going from last glacial maximum down there up into the Holocene optimum, and then you're cooling off. This is stage 5e. That was the last time it was really, really warm around the world. It's also called the Eemian. And back then, actually, in Western Australia, it seems like sea level was about 2 or 3 meters higher than it is today. And so that's stage 6, stage 7, stage 8, stage 9, stage 10, stage 11, and on going back. And there's the ice core records. And this reminds me of another French colleague by the name of Laurent Labarré. And Laurent Labarré just retired recently. He's one of the first paleoceanographers. And Laurent Labarré's law was, in paleoceanography, everything correlates with everything. And the reason for that is that everything, one way or another, is driven by this orbital forcing. Now, the second main point I want you guys to take from this talk is not only that it was a cooling from 6,000 to 10,000 years ago, but that these global forcings driven by Milankovitch cyclicity are subtle. Very, very subtle in terms of rate of change, watts per square meter over any given area for any given time. And one of the guys that's been very, very good at telling us about today's energy balance is Jim Hansen, who also happened to be one of my lecturers at Columbia in Manhattan in the early 1980s. And Jim was a young scientist then with the Goddard Institute of Space Science. He was publishing data from one of the first global climate models. And then Jim was saying already that by the year 2000, even though at that point in time it wasn't clear global warming was happening, he said by the year 2000, and I'm paraphrasing this here, turning it into the Australian vernacular, that global warming would be in the realm of the bleeding obvious. So here's what the climate data look like, or the weather data, however you want to look at it. It goes back far enough to be counted as climate, I suppose. But this is the instrumental temperature data going up till 1980. And so this would be the context he would have been speaking to me as an undergraduate. And he predicted you would leave the envelope by the year 2000. There you go. He was really spot on. Contrary to what you might hear, he nailed it. And here's the warming since year 2000. So it's all happening. Here's some of, only recently did Jim try to go back and model paleoclimate. And here's one of Jim Hansen's first attempts at that. And what he was trying to do here was put together what the climate forcings would be from greenhouse gases that you can take from the ice cores and change in albedo, as well as other orbital forcings. And then we can also calculate global average temperature from the paleoclimate data that I produce and the ice core people produce. And we get these kind of calculated temperature changes vis-a-vis the observations. And we've got a whole array now of paleoclimate indicators that the early paleoceanographers didn't have that aren't Delta 18O. And I'll show you one of them in a minute. But he worked out the relationship between temperature and watts per meter squared on the surface of the planet was about 3/4 of degrees C per watts per meter squared. So this is about a change of 6 watts per square meter over a time scale of, we got to come down here. He's a physicist, so he does this backwards from the way the paleoceanographers go. So the 0 is on this end rather than this end. So here's the last glacial maximum down here, and this is going up into the Holocene. And so greenhouse gases give you 3 watts per meter forcing, and the albedo change, largely due to the ice change, is another 3 watts per square meter forcing. And the temperature change, of course, is about 4 degrees, globally averaged. Now you have to also keep in mind that this is an average. The tropics tend to change much, much less than the higher latitudes. Higher latitudes, the changes are relatively extreme. And here's what Jim plots up for what's going to happen in the future in terms of greenhouse forcing due to greenhouse gases. And again, this is physics. You calculate how much the greenhouse forcing is going to be if you know how much greenhouse gas is going to be in the atmosphere. There are other feedbacks as well, but here we go. We've got just over the year 2000, we know that the forcing from basically the beginning of the Industrial Revolution is over 3 watts per square meter. Here's all your different forcings, and here's the temperature response, which is just trying to catch up. And the fact is there's a lag in the temperature response. Temperature response really can't keep up with the rate that we are pushing the system right now. Think about this change in terms of watts per square meter, 3 watts per square meter over 150 years versus the climate changes that I study, where you get 6 watts per square meter, and fast is over maybe 5,000 to 10,000 years. That's the difference in order of magnitude change, the rate of change that we have from the natural forcings to how we're hitting the system today. One of the chestnuts that a lot of the denialists like to roll out is, it's the sun's energy. And that's easy to shoot down because we've got good data on the sun's insolation output. And this just happens to be one of the really, really good high-resolution stuff from the satellites going back to 1980 or 78. And you can actually see the sunspot cycle in there very clearly. And the irony of this is that not only is sun's energy not increasing over this time interval, where very clearly the temperature of the Earth is increasing, but we're actually at a minimum right now in terms of the sunspot cycle and insolation vis-a-vis the sun. So there's no relationship there whatsoever. If somebody tells you that, you can say, show me the data. I'm sorry, it just doesn't exist. It'd be nice if it did, but it doesn't. Here's the hockey stick curve Michael Mann produced. And Michael Mann has been sort of the poster boy for denialist ammunition and dartboards, I think. And Probably because he had to deal with large amounts of data and lots of statistics. And whenever you get statistics involved, I remember reading a book when I was an undergraduate, it was How to Lie with Statistics. And it's easy to do that. You can sort of manipulate data any way you want. As a result, this is one of the most heavily studied data sets in terms of statistics of any climate data set ever, because this has been this raging debate ever since it was published. And one thing is clear, that even if you don't buy Michael Mann's interpretation that there was a slight cooling trend there over the past millennia, very clearly we're warming way above that trend at the moment. Here's some of my own data, and this is very, very, I suppose, typical of paleoceanographic data for the last glacial interglacial cycle. And I've got one of the new paleotemperature proxies here, which is magnesium-calcium ratio in 4 AMs. And it's more sensitive than the traditional old Delta 18O record because you don't have to worry about ice volume complications in there. And here we have, this is actually plotted with depth, but I also have C14 dates for this core, and I can tell you that this is about 10,000 years, and it goes down to about 3,000 years here. And the cooling rate for that time interval is about 0.2 to 0.25 degrees per millennium. Not per century, per millennium. And that's the kind of rate that we anticipate, both in terms of temperature increase and temperature decline within the Milankovitch force system. We just witnessed over the past century an increase in the temperature of the surface of the planet about a degree centigrade. This is unusual, to say the least. This is unprecedented, to say the least, within the context of any data set that I'm aware of, but I will show you one that might come close. So, as a result of this warming, you would expect things to happen. And the ice is melting. This is actually a relatively old graphic about Greenland ice melt, and it continues to accelerate apace. And now, I think when I first was looking at this, Greenland was melting about, in the year 2000, about 60 cubic kilometers per annum, cubic kilometers of ice per annum, losing that. By the time this was published, or just after this was published, it's about 100, it's up to about 200 cubic kilometers per annum. Greenland is shedding ice. Pinatubo was one of the last cooling events we had due to aerosols in the stratosphere, which lasted about a year, year and a half. And it did result in a global cooling, but even then, we ended up with 25 cubic kilometers of net loss of ice on Greenland. And here's a happy snap of Conrad Stefan, just to show he's legit and gets cold sometimes. Here's a set of graphics from Giff Miller, from a talk he gave several years ago, which I purloined from him. And this is from a little ice cap up near Baffin Island, which they've been tracking, shrinking. And it's sort of an allegory for a lot of the glaciers in North America. And it's gone now. The Tiger Glacier disappeared the summer of 1992. And that too is happening all over the Canadian Arctic and all over alpine areas all over the world. Here's one of our former students who's in the exploration field. He works for one of the mining companies that's taking advantage of all the new exposed rock up in Greenland. So this is a picture from Skaregard in Greenland, which is a famous layered igneous intrusion with lots of spiffy metals in it. And he says, it's fantastic, Brad. You can look at the rock walls that have just been denuded of ice, and you can actually see the minerals twinkling in the walls. There's no weathering, no oxidation in the walls at all. It's terrific stuff. What he's standing next to is an exploration core which they had put in just 3 years before that had sheared off right at the ice surface. So that was the ice surface just 3 years before in the Skaregård Glacier on the southeast portion of Greenland. And so they returned back there in 2009, and that's a picture of Tom Abraham James next to that glacier. And this is, for those of you who need to touch the wound, to see that it's not just satellite data that's showing that the surface of Greenland's dropping. That's lost 4 meters of ice over that time. So Greenland's melting, and it's melting pretty quick. It's all happening. There's the Skaregård Glacier. And for those of you who know something about what glacial ice looks like from above, you can see these ablation areas, and you can see that almost the entire area is ablating. Bright white snow would be accumulating, and there's not very much there. So it's all sort of rapidly depleting and disappearing. And that's, Tom sent me this picture, and he just put an X on there to show you where that sheared off core barrel came from. So, first set of conclusions. The Earth's system is remarkably sensitive to even very, very small changes in the energy balance of the Earth on these Milankovitch timescales. We should be cooling. This is one of those fundamental things we learn in paleoceanography as a second-year student, but we're not anymore. Conservatively, we're hitting the Earth system with an increase of at least 3 watts per square meter in the lifetimes of everybody sitting in this room, sort of from the oldest to the youngest. And that's an incredibly big hit on the Earth system, which is half of the entire interglacial change in watts per square meter received by the surface of the planet. The Earth is certainly warming. There's no denying that. And the ice is melting. There's no denying that. Now, I'm going to shift to the last time we think that the Earth was hit with something similar to what's going on right now. And to do that, we have to go back to a time interval we call the Paleocene and a time interval we call the Eocene. This is about 55 million years ago. And they're calling this event the Late Paleocene Thermal Maximum. And within this time interval, we had this increase about 4 or 5 degrees C within the space of about 10,000 years, which is abrupt for geologic records and is about as high a resolution that we can frankly attain given the sedimentation rates that we can find around the world in pelagic sequences. At the same time, we had this big negative kick in delta 13C, which is the ratio of carbon 13 to carbon 12. Methane tends to have a very, very negative ratio. And to cut a long story short, the most logical, ceteris paribus, easiest way to do this is to release a whole lot of very negative, in other words, very low carbon or methane with a very low abundance of C13. And so methane fits that bill, biologically produced methane. And we've got a lot of that around, actually, within the Earth system, set in the slope sediments of the world. They're called methane hydrates. And there's about 10,000 gigatons worth of carbon wrapped up in those things. And they're still frozen there today at about 400 to a kilometer water depth. And it's a lot of carbon. And all you have to do is heat that area up, and we'll release that carbon. But don't sweat it. It can't possibly happen given the rate at which the ocean can possibly warm for several millennia, probably. But we might get there given the rate we're going. And then you get a big burp in methane over on top of the whole warming that we're already inducing on the system. Now, this is one of my buddies, Jim Zakos. We did postdoc together at Michigan. And he's been one of the big, basically, he's published, I don't know, probably half a dozen papers on this Paleocene-Eocene thermal maximum and done the carbon cycle modeling. Looks like it's about 2,000 gigatons of carbon. Atmospheric CO2 doubles in this time interval, and the temperature increases about 4 or 5 degrees. And that's off a very, very warm temperature base. And this is what it looks like at high resolution. Where you're coming along here, and you've got bottom water temperatures, which are 8 to 10 degrees, and then this system gets hit with this negative carbon, and the temperature goes way up. These are bottom water temperatures. This means this is high latitude temperatures, because this is where these waters are formed, up to 14, 15 degrees, and then it decays off in a very predictable manner back down to your baseline. Now, there have been a lot of publications since Jim highlighted this, where people have gone in and targeted these time intervals and looked at how warm it actually got. And this shows several calibrations of a new paleotemperature proxy called Text86. I like this temperature calibration in the orange much better than the one in the red. But the green one's not bad either. But what a lot of these calibrations are telling us is that the temperature jumps from a background temperature, in this case, in the Gulf Coast of Texas, or Mississippi actually, from 27, 28 degrees up to 34 degrees plus. And it's maintained for the interval of that warming interval. Now, that might not sound too remarkable to you, but I can tell you that we don't understand how surface water temperatures can get above 31, 32 degrees C. Because once surface water gets to be that temperature, typically it evaporates, and that evaporative cooling modulates the temperature and keeps it acts as a thermostat, keeps it from warming any higher than that. So these data are disturbing. And I've sailed up in one of the warmest regions in the world. That's the one off Melville Island up in the Timor Sea. And it's interesting because the engines of most ships are water cooled. And when temperature of the water gets up above 30 degrees C, those engines can't cool anymore. And you have to sort of puddle along at like 3-4 knots. Otherwise, the engines will overheat. The air conditioning breaks down. And so you're standing in the steam bath, quite literally a steam bath, because it's evaporating as fast as it can, that temperature of surface water. So there's no doubt that this is really, really warm. We've got data from the Arctic now that shows the Arctic, the cool months in the Arctic were about 20 degrees C during this time interval. The differences are spectacular. One of the only ways we can imagine that you can raise surface water temperatures above that 31 degree threshold is to make the atmosphere relatively stagnant. So you can't move the water vapor away from that surface of the water. One way you can make the atmosphere stagnant is by dropping the pole to equator temperature gradients. And you can do that if you hit it with enough greenhouse gases and make it cloudy enough at the poles. So that's our look at the Paleocene, Eocene. We are in the midst of doubling CO2 right now. It's almost guaranteed 3 or 4 degrees of warming. Lots of ice is going to melt. Pretty confident of that as well. And sea level will rise. No doubt about that. I haven't talked to you about the lags that are in the system, but there is a tremendous lag in the system. In other words, if we stop putting CO2 into the system right now, just turned off every fossil fuel producing machine on the planet, we'd still be warming for probably half a century. The rates at which this is going to happen is still debated, but temperature and CO2 right now are rising faster than we have any analog for in the past 65 million years. Thank you.
Okay, so we'll take questions from the audience. If you could wait until Francis brings you the roving mic until you ask Brad the question, that'd be appreciated. Okay, yep, start down the front here.
Hi, my name's Phil. Now, we've had the there's a possibility that we've reached our peak as far as temperatures and greenhouse gases can go. And the other issue is Ewing and another fellow did in the 1950s, predicted a theory that as ice melts in the northern hemisphere, it then reverts back towards, over time, a more glacial, towards more glacial type conditions. So with those three, what would you say to that?
Well, I'd say that certainly we haven't reached a peak in temperature or CO2. We're emitting CO2 at a rate of 8 gigatons per annum. And of course, we're going to be reaching new peaks in CO2 as long as that continues every year, on and on and on into the future. And that doesn't look like it's abating. Odds are we'll be getting to probably 20 gigatons per annum in just the space of decades if things keep going the way they are. So it's nowhere near a peak. The glacial things that Ewing probably were talking about were on a much longer time scale. So one of the things that we really don't understand is how some of these big glaciations are initiated. And some of the modeling that some of my colleagues, David Archer for one, has produced, the fact that we put so much greenhouse gas in the atmosphere, we will have overwhelmed the Milankovitch cyclicity for a time scale of probably about 100,000 years. So you don't have to worry about glaciations, probably on that order of magnitude. Mini Ice Age was a regional North Atlantic thing. It's not really a global event.
Another question over there.
Oh, right. Your slide showed that in the last 4 interglacials, the temperature was about 2 degrees centigrade more than now. Can you give any information about how far the ice retreated at those times?
Well, it probably was... No, it's quite clear the Eemian was warmer than pre-industrial. We're basically approaching Eemian temperatures right now. We're actually in the Eemian time. We're actually at Eemian temperatures right at the moment. We've come off that temperature base, and we're back at temperatures that were like the altithermal early in the Holocene as well, which was also over a degree more than pre-industrial. So we had this cooling from the altithermal, and so we've just come back up to that temperature band. Within the next decade, we will have exceeded the temperatures from both the Eemian and the altithermal. Given that we've got some pretty good data from Western Australia, for example, that you've got 2 or 3 meters of sea level rise above what we have today for the +2 degrees or so for the Eemian. Odds are most of that melting came from, our best guess is that it came from Greenland and the southern half of Greenland rather than the northern half. But that's hard, it's hard to pin down exactly where that ice melt came
I'm sorry, I don't have the knowledge to ask a serious technical question, but there are climate change deniers out there. I might mention Professor Rob Carter. He is often heard on the radio, and he is expounding that there is no anthropogenic global warming. I've spent this afternoon in the National Library photocopying a paper of his, which was published, and following that, a reply by Professor Will Steffen of this university, and then followed by that, another reply from Professor Rob Carter, who's a geologist. I'm just wondering if you could put my mind at rest so that I don't have to read these papers.
I don't think it's really, I think I like to let the data talk for itself. I showed you what the data are. Clearly, climate is warming. Clearly the ice is melting. Clearly we're pumping greenhouse gases into the atmosphere. I know Bob Carter. I know him personally. And perhaps in private I could speculate about why he's saying the things he's saying. But I don't really want to get into that sort of thing, just from a personal point of view. But I don't think he has any physical basis to, from a physics point of view, to say what he's saying. And none of these guys really have any data to support what they're saying.
Thank you. Tony Eggleton. James Hansen, at the end of his book, seems to suggest that the oceans are going to get close to 100 degrees C. Do you know how he gets that much greenhouse gas effect?
I must admit I don't agree with Jim in that. This book is Storms of My Grandchildren, and he's really taking a worst case scenario where if you do warm up the thermocline like I was talking about and you release the 10,000 gigatons of methane that are locked up in the slope sediments, then you could maybe get this runaway greenhouse. But I think that there are a lot of feedbacks in the system to overcome that. So I don't think we're going to push the system that far. At least that's my hope. But it's important to raise the point, I think, that that's within the realm of possibility, even if it's within the distant possible scenarios. We're talking thousands of years down the road. It is a worrisome possible endgame if you got all this greenhouse gas into the system all at once. But I think that's going to be unlikely.
Doug McKenzie. The issue of methane locked up in things like the tundra in North Asia. What's your comment on that?
Well, clearly there is a lot of methane up there, and I've been seeing some of the YouTube videos that actually my son found, these guys sort of lighting it on fire. You know, these guys will find one of these methane seeps in the Arctic tundra and hit it with a lighter that will go poof and explode just locally. And so that is a flux, and I actually took out the graph from this talk of the methane rise over the past century. Fortunately, for whatever reason, the rate of methane increase is decreasing, not increasing in a relative rate, as opposed to CO2, which is increasing apace. And the amount of methane actually in the Arctic is still poorly quantified, but it is a danger. And there's obviously going to be a lot of it there. And it's not just methane in the Arctic or methane in the Arctic that you have to worry about. It's actually all that organic matter wrapped up in peats, et cetera, that represents a huge amount of carbon that doesn't oxidize because it's not warm enough for it to oxidize. And it will oxidize as the temperature rises. And that band up there in the Arctic is where most of the warming is taking place. So it does represent a significant feedback, there's no doubt.
Sorry, I don't remember what the source was, but it showed temperature lagging. It showed CO2 content lagging a change in temperature, and so it's suggesting that the temperature changes to do with the intensity from the sun.
Well, that's exactly right, and that's what the Milankovitch cyclicity predicts. You see, the Milankovitch forces the temperature change. That's the solar cycles. So it's absolutely true that the CO2 is a secondary feedback on the system, in the natural system. But it's still an amplifier, okay? What's different now is that we're forcing the system with the CO2, but it's still an amplifier, okay? Yeah.
I know you didn't talk about the acidity of the ocean, but...
yeah, I'll save that for talk maybe next year.
Yeah, okay.
I'll give you an acidity talk.
Quick question. A number of weeks ago there was this suggestion made that the acidity of the ocean could be addressed by dumping large quantities of, I think, iron oxide into the ocean. I just wondered, did you hear of that?
Well, that's a furphy that's been around for a long, long time. The short answer is no, that's not going to happen anytime soon. But there's also a much, much longer answer to that. But it would also be very, very expensive to go out and dump a lot of reactive iron into the ocean. Fact is that if you wanted to actually keep CO2 drawn down by that method, you have to keep adding iron. You have to keep it up, because once you stop, all that CO2 just burps back up.
I just have one last question.
Thank you. Simon Veach. Brad, you talked about feedbacks and lags.
Yeah.
What about thresholds? And do you think we've got enough knowledge about what those are? And if not, what sort of research do we need to do to fill our gaps in knowledge?
Well, I suppose that's one of the reasons we do concentrate on things like the Paleocene-Eocene thermal maximum. Obviously, it was a very warm time, and they didn't reach the kind of Jim Hansen type threshold where we turned into a Venus type planet. Now we're desperately trying to keep up with what's going on right now. In a sense, the system has gotten ahead of us. The changes are all happening so fast. It would have been nice if somebody had warned us 50 years before that we were going to conduct this experiment on the system. But in a sense, the whole scientific community, in terms of people that do carbon cycle modeling, climate modeling, we're all just trying to keep up. But I think the short answer to that is that the precautionary principle should apply here, that we really don't know what those thresholds are, and therefore we should be cautious. Well, I think Michael Roderick is in the audience here, and one of the things that will help us determine the sensitivity of the system are these new Argo floats that we have in the ocean, which are showing how the energy is being distributed in the ocean. That's really, really very important, because we're still just coming to grips with that. The other is still those satellite data sets for imaging how the heat is moving around the globe. And still, in detail, we still have a lot to learn about how that transport is taking place, and both within the ocean and within the atmosphere. So those lines of research are critical for finding out about what the heat flows are, but that doesn't really address what the thresholds. And the thresholds, unfortunately, really have a lot to do with ice dynamics, which is really, really difficult to perform experiments on. It's been very entertaining, actually, from a scientific point of view, to watch the glaciologists over the past decade suddenly go to places like the AGU meeting in San Francisco and go, oh God, we were wrong. Suddenly that ice is moving a lot faster than we ever anticipated just 5 years before, because about 2000 they were saying, oh, Greenland couldn't possibly melt for thousands of years. And then 5 years later they were going, well, we got that wrong, and it's moving a lot faster than we thought. So we really don't know. And I guess one of the places you want to study a lot more intensely would be the ice sheets themselves, and see how they're responding to this change. Yeah.
Thanks. Well, would you like to join me one last time to thank Brad?